discussing about signaling over additive white Gaussian noise channels. So in any communication system, additive white Gaussian noise will be there along with the transmitted signal. The study of the effect of additive white Gaussian noise on the signal is required for taking correct decision at the receiver. Geometric representation of signals is a very useful method for taking a correct decision at the receiver. So let us try to understand the geometric representation of signals. So geometric representation of signals is a method for representing m number of finite energy signals as a linear combination of n orthonormal basis functions. So Si of t is the m finite energy signal where the value of I can vary from 1 to m. So I can express this m finite energy signals as a linear combination of n orthonormal basis functions, whereas the basis functions are represented as phi j of t. So where the value of j can vary from 1, 2, and so on up to n. The number of orthonormal basis functions always less than or equal to the number of finite energy signals. So n is less than or equal to m. So as I said, the geometric representation of signals is a method to represent m finite energy signals as a linear combination of n orthonormal basis functions. So I can express Si of t is equal to summation j is equal to 1 to n Sij phi j of t, where this Si of t exists over the interval 0 to t. So let me call this as equation 1, where Sij is the coefficient. Okay, so Sij is defined as Sij is equal to integral 0 to t Si of t phi j of t into dt. This also exists over the interval 0 to. So let me call this as equation. So the basis functions, let us try to understand the orthonormal property of that. So the basis functions form the orthonormal basis, that is integral 0 to t phi I of t phi j of t into dt will be equal to 1 if I equal to, and it will be 0, I is not equal to. Let me call this as equation. The first condition of the equation 3, that is phi I of t into phi j of t into dt over the interval 0 to t will be equal to 1 if I equal to j, forms the basis functions are having unit energy over the interval 0 to t. And the second condition, that is I is not equal to j, so their product is 0 over the interval 0 to t. That indicates that these two orthonormal basis functions are orthogonal to each other. So first condition talks about the unit energy, that is condition 1, and the second condition talks about these two phi I of t and phi j of t are orthogonal to each other. So I can represent this m finite energy signal, that is Si of t, as a signal vector Si. So Si will be equal to Si1, Si2, and so on up to Sin. I can represent the m finite energy signal as a signal vector known as Si. Okay. So which is equal to what? Si1, Si2 and so on up to Sin. This Si1, Si2 and so on up to Sin are the coordinates of the signal vector Si. So this Si is called the signal vector. Si is called and this Si1, Si2 and so on up to Sin are the coordinates of the signal vector Si. So the signals S1 of t, S2 of t and so on up to Sm of t are the m points in the signal vector S1, S2 and so on up to Sm. So these m signal points are known as the message points in the Euclidean space. Okay, so the Euclidean space is formed with the basis functions pi1 of t, pi2 of t and so on up to pi n of t. Euclidean space, or it is also known as the signal space. Vector Si is called the signal vector. Okay, Si can also be regarded as a point with coordinates Si1, Si2 and so on up to Sin in an n-dimensional Euclidean space. Thus, the signals S1 of t, S2 of t and so on Sm of t can be considered as m points represented by the vectors S1, S2 and so on up to Sm in an n-dimensional Euclidean space with reference to axes phi1, phi2 and so on up to phi n. So the n-dimensional Euclidean space is also called signal space, and the representation of signals in an n-dimensional signal space is also called as signal constellation. The representation of signals in an n-dimensional signal space is also known as signal constellation. So this is a very important term, and we draw the signal constellation diagram for every digital receiver circuit. Okay, for every digital circuit we draw the signal constellation diagram. So based on the signal constellation diagram we will be able to decide which symbol is transmitted and where the symbols are transmitted by looking at the signal constellation diagram. So let us take one example how to draw the signal constellation diagram for the given message points. So the problem is, let us consider the signals, that is S1 of t. Let us consider three signals, is S1 of t, then S2 of t and S3 of t. So these three signals are represented with reference to the two basis functions, that is pi1 of t and pi2 of t. These three signals are represented with reference to two basis functions, that is pi1 of t and pi2 of t. The coordinates of these three signals is given as, that is S1 is equal to S11 comma S12, so which is equal to 3 comma 0, and S2 S21 then S22 which is equal to minus 2 comma 3, S3 is equal to S31 comma S32 which is equal to minus 3 minus 3 comma minus 3. So these are the three message points S1, S2 and S3, and its coordinates have been given. So for first one S1 as S11 and S12, it is 3 comma 0, and S2, that is S21, S22 which is minus 2 and 3, and S3 and its coordinates are S31 and S32 and its coordinates are minus 3 minus 3. So we need to draw the signal constellation diagram, and we need to express these three signals in terms of the orthonormal basis functions. So let us try to understand how to represent these three signals in the signal constellation diagram. Since there are two basis functions, so I can take this as phi1 of t and this one as phi2 of t. So I can mark the scale, that is 1, 2, 3, 1, 2 and 3, then minus 1, minus 2, minus 3, only minus 1, minus 2, minus 3. So that is 1, 2 and 3. This side minus 1, minus 2, minus 3. Similarly 1, 2 and 3. Minus 1, minus 2, minus 3. See, first one is 3 comma 0. So 3 on x-axis, that is phi1 axis, and 0 on phi2 axis. So this is my S1. The next one is minus 2, 3. So minus 2 is this point and 3 is this point, phi2. So I think I can consider this as my S2. Then third one is minus 3 and minus 3. So minus 3 is this point and minus 3 is this point. So I can consider this is my S3. I can draw from the origin. This is my S1 vector. Then this one is my S2 and this one is my S3. So this is what is the signal constellation diagram. Now, how do I express this as an orthonormal? Means these three signals need to be represented in terms of basis function. So to do that, so I can write S1 of t is equal to, since it is first on phi1 axis, it is 3. So I can write 3 into phi1 of t, and phi2 of t is 0. So 0 into anything is 0. So I can leave that. Then S2 of t, which is equal to what? Here phi1 is minus 2 and phi2 is 3. So I can write minus 2 phi1 of t plus 3 into phi2 of t. And S3 of t is equal to, so phi1 is minus 3 and phi2 is minus 3. So I can write minus 3 phi1 of t, then minus 3. So this is how we express the m finite energy signals as a linear combination of n orthonormal basis functions. So this is one just example. How do we construct the signal constellation diagram and how do we express for the given signals in terms of the orthonormal basis functions. So here the value of n is 2 and the value of m is 3, because I have 3 signals and 2 basis functions. So now let us try to construct, that is, as I said, here Si of t. Si of t is expressed as what? Summation j is 1 to n Sij pi j of t. That is, I am expressing m finite energy signals as a linear combination of n orthonormal basis functions. As I said, Sij is the coefficient which is defined as Sij is equal to integral 0 to t Si of t into phi j of t into dt, right? And I said the basis functions, okay, the n orthonormal basis functions forms two or exhibits two characteristics. One is their product will be equal to 1 if those two orthonormal basis functions values are same. That is, if I equal to j, then it exhibits the property of having unit energy. And if I is not equal to j, then we say these orthonormal basis functions are known as means they are orthogonal to each other over the period 0 to t. So let us try to construct SI of t diagrammatically. Means from the coefficients, and each coefficient is multiplied by the different basis function, how do I get the SI of t? Similarly, from the basis function and as well as the coefficient, how do I get back SI of t? Say SI1, which is multiplied by then SI2, which is multiplied by the basis function by 2 of t, and so on up to SIN is multiplied by the basis function by n of t. So all can be summed together. I can say it is SI of t. Okay, whatever the equation 1, what I have written mathematically, can be represented with the block diagram like this. Means each coefficient is multiplied by a respective basis function, like that all those coefficients multiplied by a respective basis functions are summed together to get SI of t. So this is known as the synthesizer, because it synthesizes coefficients with the basis function to get the desired energy signal, that is SI of t. So from SI of t, how do I obtain the coefficients, that is SI1, SI2 and so on up to SIN? So here SI of t is the input. This SI of t is given as one input to the product modulator, and that is multiplied by a basis function by 1 of t. Then I am integrating the product over the interval 0 to t to dt. So here I will be getting SI1 like that, or another one will be by 2 of t. The product of those two will be integrated over the interval 0 to t into dt. I will be getting the output as SI2. So like that it can be extended for nth basis function. So by n of t. So this we call as analyzer. Known as the analyzer. So from SI of t, I will be able to obtain the coefficients SI1, SI2, so on up to SIN. So this one is known as synthesizer, because it synthesizes the coefficients with the basis function to get the energy signal SI of t. So this is all about how do we represent the equation 1 and equation 2 diagrammatically. Okay, so let us stop with this. Let us continue in the next class for proving that the signal energy, how it is related with the square length of the signal vector. Okay.